And then in an observational study, you might still have knowledge, right? Because you can talk, maybe let's say the doctors assigned the treatment, and you talk to the doctors and you ask them, how do you make these treatment decisions? What variables do you take into account? It was a huge effect in the observational data. Mm-hmm. So that gives you then, if you tell people that, they say, and then you look at your data, you see that everybody who doesn't take the treatment doesn't get cured. It's almost 100% no cure. Then you start realizing, wow, right? This is clearly very significant, even though the study had all kinds of problems. What is a plausible causal gap? Now that's where you can play all kinds of games. And that's where these different ideas can come in. And one is, of course, negative controls can be helpful. That will also give you an idea that you could say at the end, my causal gap has to be 3 times as big as the impact of these particular confounders in my data set. So you have to believe that the unmeasured confounders out there are much stronger than the measured confounders to still wash away this finding.
What's your favorite sensitivity analysis approach?
Hey, Causal Bandits. Welcome to the second season of the Causal Bandits podcast, the best podcast on causality and AI on the internet.
Early on in his life, he was only interested in 2 things, chess and tennis. Today, his inspiration comes from real-world problems. He's driven by a large-scale vision, not stepwise thinking. The godfather of TMLE, professor of statistics at UC Berkeley. Ladies and gentlemen, please welcome Professor Mark van der Laan. Let me pass it to your host, Alex Molak.
Welcome to the podcast, Mark.
Thank you. Pleasure to be here.
It's a great pleasure to have you here. You're such a big name in the community, and I'm very, very excited that we finally managed to meet and that we can have this conversation and share it with the community.
Excellent. Yeah, I'm looking forward to it.
So I would like to start with a topic that some of our listeners will be very, very familiar with. Some others may be a little bit less. Nevertheless, I think that's an important topic and also hopefully interesting. And it's the idea of this causal roadmap. So when we think about traditional machine learning projects in industry, for instance, we have some steps we do to make sure that the output, the solution that we build will be of good quality. When we do statistical analysis, when we design a study and so on, we also have certain steps to check out to make sure that, our randomization is correct, and so on and so on. With causal inference, especially with causal inference from observational or mixed data, this picture gets even more complicated. And we have some authors, starting maybe with Judea Pearl, and then people like Amit Sharma, the author of the DUI library, who try to pin down, so to say, this process and encapsulate into a finite number of steps that could make it easier for people, for practitioners, to grasp what's going on in this process of causal inference. You also proposed a roadmap with your colleagues. Can you tell us a little bit more about your vision of the causal inference roadmap, and in particular, the role of uncertainty, plays in this roadmap?
Right. Yeah, we call it the roadmap for causal learning or targeted learning as well. Is very important for us and has played a big role in anything we do really, and also in our curriculum for the students. And the basic steps, as we've stated them, are step 1 is you have to realize that your data is the result from an experiment. So you have to describe the experiment which generated the data. And then with that, you can also start describing the kind of causal question you have. And so that's step 1, is just coding the data. You might already give it some notation, because you probably have in mind a causal question. And with that causal question, there are certain definitions of what you might call the treatment. And there might also be things like censoring. And so that we give special notation, so that these variables, they are so-called intervention nodes in causal inference. And so this way we start describing the data pure in a notation so that we can start naming variables and refer to them. Like, for example, if you go to Jamie Robbins' early papers, he would use the notation, over time, L of t and A of t. And L of t would be everything you measure at time point t or an interval t, such as time-dependent biomarkers and outcome process. And then AFT is used for the treatment at time t, and maybe also, and then you also have censoring. But that's step one. Then step two is describing the likelihood of the data. And by the way, there's slight difference in orderings, how people present the ordering. Some start with a causal model. In this case, I say, let's write down the likelihood of the data. Now, what you typically do there is you just say, okay, how was the data collected? Was there time ordering? Did we first collect this, then that, then that, then that? And so that's already getting towards somewhat what you might think about a causal model. But usually this is just known. You just know things were collected over time. And so that helps you, because your causal inference is getting hard if you don't have in time ordering. So when you describe the likelihood, you start also thinking about, what do I know about my likelihood? Right? Like in traditional statistics, we talk about maximum likelihood estimation. So which means you need a model. And we call that a statistical model. And a statistical model involves, in this case, where you say, okay, what's the next variable? Like conditional probability of the treatment assigned to the person given the history. What do you know about that? That's, for example, knowledge. Of course, in a randomized trial, you would actually literally know it completely. It would be a flip of a coin, and it would be a marginal probability. You might have more advanced sequential randomized trials where you still know it, but then these probabilities are learned from the past. And then in an observational study, you might still have knowledge, right? Because you can talk, maybe let's say the doctors assign the treatment, and you talk to the doctors and you ask them, how do you make these treatment decisions? What variables do you take into account? That's what we call conditional independence assumptions, where you say the treatment is independent of the history given these key variables. So that's incredibly important knowledge. If you have that, that makes actually an observational study as powerful as an RCT, because now with some extra challenges, but then you also can compensate that with larger sample size. That's the statistical model. So that's just writing down essentially the likelihood as a product over time points of conditional probabilities, what you observe next given the past, and what do you know about them? Then comes the next question. What is the feature we're trying to learn from the data? And that's what we call the statistical estimate. Now that's challenging, and that's why you need a process for that. And that's where we then get into defining a causal model, which is kind of represents a perfect world where you can observe everything you like to observe. And so, for example, in causal inference, there's the so-called Neyman-Rubin model or the structure equation model. But basically, it allows you to define potential outcomes. Like for every subject, you can think of, I might have an outcome under one treatment and an outcome under another treatment. So that defines what we call full data. Right? It's the perfect data you would have liked to observe on everybody. And then in that world, you define a feature you're trying to learn, which is now a causal estimate. It's not something you necessarily can learn from the observed data, but in that perfect world, you could have. So that helps a lot, because then with your collaborators, you can sit down and define the real question and define it in terms of like a hypothetical experiment, like a hypothetical randomized trial or a perfect world where you can collect all these potential outcomes and then say, what do you really want? Now we have defined a causal estimate. You can think of a simple ATE, average treatment effect. And then comes the next reality check. Okay, how are we going to identify that from the observed data distribution? And so in other words, how can we go from the likelihood of the data we can learn towards that causal quantity, where you get so-called identification results? And these are, part of what causal inference is about, is establishing identification results. And so there are a lot of them out there, right, based on known measured confounder assumption. There's the so-called G computation formula, or the longitudinal G computation formula, Robbins 1986, and there are also identification results based on instrumental variables and so on. It's like a theorem. It says, I can describe this causal quantity as a feature of the distribution of the data under the following assumptions. At that point, you have defined a statistical estimate, something you can learn from the data, which you can claim to be equal to the answer to your causal question, in case these assumptions hold. Now, at that point, you might have to discuss what you think about these assumptions. It might drive you to say, we can do better. Let's collect some more data or think about another type of experiment. But either way, at some point you say, this is it. This is what I want to do. You have some sense of what we call the causal gap. which is the difference between the statistical estimate and the causal estimate. Sometimes you just know it's equal, great, no causal gap. And sometimes you say, well, I have maybe some sense, that's pretty good, so I'm moving forward. At that point, the statistical estimation problem is defined. You have your likelihood, you have your statistical model, and you have your statistical estimate. And so now comes the question, the estimation step. Right? So overall, what I've talked about currently is describing the experiment, describing the likelihood, describing your statistical assumptions, your statistical model, and through a causal model and identification result, also describing the statistical estimate. At that point, estimation becomes the next step. Now, the estimation step is another thing where we are very precise about it by saying it has to be a priori specified. In other words, something which plays with the data and tries left and right is not an estimator. So an estimator is an a priori specified algorithm you're going to apply to the data. You hope it gets close to the statistical estimate, so the answer to your question. And you also hope that it has a way to understand its sampling distribution. Right? So there might be like a central limit theorem, and you might have an approximately normal sampling distribution. Now, that's kind of how do you construct such estimators is then a whole field. And in particular, there's efficiency theory, which talks about what will be an optimal estimator from an asymptotic perspective. So these are called asymptotically efficient estimators, so that they do not only approach the truth, they approach the truth at the typical rate, like 1 over square root sample size. But moreover, more importantly, you can use it to construct confidence intervals, and they have also minimal variance, asymptotically at least. So that's where there's a lot to say about that, and probably we're going to talk a little bit about that, how you do that. And that's actually has been a big part of my journey, has been understanding that problem from a PhD thesis, starting about understanding non-parametric maximum likelihoods to working with Jamie Robbins and so on, understanding the kind of estimating equation approach. And then eventually we came up with TMLE as a kind of a sophisticated way of generalizing what people do in traditional statistics, but then also making it possible to do it in these realistic models. Because that's another point. When I said, what are your statistical model assumptions? What do you know? That's a real question, right? It's not a model out of convenience, right? So that's why that model is taken very seriously, and it's supposed to be realistic, meaning it will never be a parametric model. It will always be what we think of as an infinite dimensional models, where you might have knowledge, like conditional independence assumptions, but you don't have knowledge up to a finite dimensional parameter, like in a logistic regression or something. So that's why when you do the estimation, it will recognize, hey, this estimate, like the AT, depends on the conditional probability of death, as if that's the outcome, as a function of the treatment and the covariates. So I have to learn that. So that's where machine learning comes in. But then you plug that in the ATE, and then you want to have the right properties.
I want to ask to quickly talk a little bit more about uncertainty, because in causality, in causal inference, right? And I remember this is a part of your roadmap. This step regarding uncertainty quantification, it's not really one step, because we have more than one source of uncertainty, right? We can think about conformal prediction maybe, and we say like, okay, under exchangeability, this will be our quantification of uncertainty. But here we have also what you mentioned. We have also uncertainty regarding the identification itself, and so on. So we might have different levels. What's your take on that?
That's also why the roadmap is so important, because it addresses all these different levels of uncertainty. One is, of course, the formulation is so important. That's why I talked about these first steps, because if you don't get the formulation right, that's the start of everything. And then you're probably already off. And then you have no idea what you're doing. So what's uncertainty at that moment, right? We need to know precisely what the target is. That's why we have the causal estimate. Then we get the identification result. That creates one level of uncertainty, which is the causal gap. But at least we know what we're talking about. You have an actual real target. And then comes the statistical uncertainty. And that's what the estimator is. And that's where we have to get valid confidence intervals. And so that's another level of uncertainty. Of course, the statistical estimation and the confidence interval construction, they take care of, at least if you do it right, you can get a confidence interval with good coverage for the statistical estimate. But then you still have that other uncertainty, which is the causal gap, might be there. And that's where we use a final step. Again, this is all recognized by the literature, and what we call sensitivity analysis step. And that's where you start moving towards real conclusions.
What's your favorite sensitivity analysis approach? Which one do you think is most useful?
There's this so-called, in the past there were these kind of more parametric model-based sensitive analysis, and I didn't like them. So that's why we defined at the time, non-parametric sensitive analysis. But in particular, that leads to an interesting plot, which I think is a great starting point. And that is that you put on the x-axis, it's an xy plot, and on the x-axis you put the causal gap. So you say if the causal gap is 0, what will be your confidence interval for your causal quantity? Now that would just be the confidence interval from your statistical estimation. So you can say if the causal gap is 0, this is my statistical conclusion. The truth is somewhere in this confidence interval, and I might reject the null or look at the confidence interval. What if the causal gap is this much? Then you can essentially just shift the confidence interval. And then it will be under that kind of causal gap, it would be the confidence interval. And so now you can make a whole plot where you see all these confidence intervals shifting. And you might see if the causal gap is positive, then it shifts towards the null. And at some point, it might actually include the null hypothesis. And so in particular, you can ask the question, how big can the causal gap be and still have a significant finding? And we call that the G-value. Mm-hmm. And so that you can now conclude at the end of the day, if you trust your statistical confidence interval, you can conclude that the causal gap can be this big and you would still have a significant finding. Now then comes the next thing is, okay, how big is that? Right now you have a number. Now you need to kind of understand, this will help you a lot actually already, right? Because you get a sense, oh, wait a minute, this is like 20% of the relative risk or something. So you get some sense of, is this important or is this kind of borderline anyway? And again, keep in mind what you know based from the experiment, how precise the experiment was, if it was careful, did you collect the confounded? But anyway, then you have another layer where you try to get towards what is a plausible causal gap. Now that's where you can play all kinds of games. And that's where these different ideas can come in. And one is, of course, negative controls can be helpful, right? You might have a negative control treatment or a negative control outcome. You can redo the whole analysis, the same estimator on that data, and see what happens. And if you see that the confidence interval, and the estimate is kind of away from 0, then you might have some bias, causal gap there. And that might give you a sense of the size of causal gap, which might be plausible. Of course, then it all depends on the negative control being, having similar confounding structure, but at least you get a sense. Other things we also do in your analysis, leave out some key confounders, the ones you measure actually, and then see what happens with your change in estimate and confidence interval. And that will also give you an idea that you could say at the end, my causal gap has to be 3 times as big as the impact of these particular confounders in my data set. So you have to believe that the unmeasured confounders out there are much stronger than the measured confounders to still wash away this finding.
How can you quantify this causal gap? For those people who are not familiar with this approach, what intuition could we give to them? What is on this x-axis? What is the meaning of this number?
Yeah, if I tell you let's say we are estimating an average treatment effect, I'm seeing whatever our estimate might be in difference in proportions being like 30% or so, and then with a confidence interval. Yeah, then a causal gap could be, at the end, 0.1, 0.2, 0.3. So these are numbers, but how do you interpret them is then one question. And so one way, again, and these are things where people can be creative. Some people like simulations, right? Where you kind of simulate things and see what that says. But what we also like is that we are creating a unit which corresponds with, for example, if I leave out all confounders, the measured confounders, and redo my analysis, how would my estimate change? And that change in estimate, we make a unit. And this can be done with all confounders, but also be done with a subset of the key confounders. And you say, and your unit becomes now that you say, hey, 1 unit means I'm getting this difference in my estimate due to leaving out that group of confounders. And then you can measure that so-called G-value, which is this maximal size of causal gap, which would wash away your finding. You can say, hey, it's 4.5. That corresponds with, you have to believe that causal gap is 4.5 times as large as the change you would see by leaving out some key confounders in your data set. So that's how you can help to get some sense because that's kind of what people have to think about. Okay, what confounders did I maybe miss? Are they kind of comparable in impact with some things I've measured, right? And that might give you then some sense of getting your head around it. But anyway, so that's one approach which you can carry out, but there are others. I mean, like in our original paper, we actually did a real analysis. There was a paper with Ivan Diaz, and it was on Chagas disease. And it was actually a company which came to me and said, okay, we want to make this drug. We have this drug, and we want to produce it in the United States. And so the problem is we cannot run a randomized trial here in the United States because the drug is already used out there in Latin American countries. So there's observational data, which clearly suggests this drug is very effective. So how can we do this? Right? How can we talk to the FDA about this? And so that's where, at the time, we formulated this sensitive analysis. And so there, we did this, what I just described, right? But also we were able to bound the causal gap by something which is more interpretable. So we could, in that case, it was about, there was this treatment versus control. It's actually very long-term outcome, right? People get this parasite, and it takes sometimes 30 years to really develop all these hard problems. There was observational data out there, and you have then, like, essentially it's a binary outcome, some kind of death or developing this heart disease, and you can talk about the cure rate, right? If you take the drug, what would then be your cure rate? Versus if you don't take it, then essentially it's zero because you never get cured. And so we were able to bound the causal gap by the counterfactual cure rate if everybody doesn't take the treatment. It's counterfactual cure rate under control. And that was like a number and then we did the G value in terms of that, right? And so we could show that you had to believe that the causal gap you had to believe that the counterfactual cure rate under no treatment has to be 45% in order to wash away this finding, because it was a huge effect in the observational data. So that gives you then, if you tell people that, they say, and then you look at your data, you see that everybody who doesn't take the treatment doesn't get cured. It's almost 100% no cure. Then you start realizing, wow, right? This is clearly very significant, even though the study had all kinds of problems, right? Because that's missingness, had the unmeasured confounding, but it becomes obvious, right? So that was an example where, that it was possible to be very conservative in the bounding of the causal gap by something which was very interpretable, so that even biologically you say there's no way. Right? But you cannot always do it but that's the kind of things you sometimes can do. But so at the end, the transparency is important, right? Because that's where other sensitive analysis, sometimes they start doing these, you assume all kinds of, like you assume a Cox model for your failure time, and then you put in some kind of covariate, which is a counterfactual failure time under no treatment, and then you talk about the coefficient of that, how big that is. If it's zero, then there's no unmeasured confounding, and if it becomes such a mess that people don't even know, right? It's not a smoke curtain you throw out there, and at the end, it's not helpful. And so I think it's very important to stay very transparent, and so that people can follow what you're claiming, and that's, I think, possible with this kind of non-parametric sensitive analysis.
That's very great. You mentioned the importance of transparency, and I think the roadmap you shared with us before, similar to other roadmaps in my opinion, proposed by Pearl, by other people, all of those roadmaps help practitioners and researchers to be more transparent. And I like to say, that the transparency is one of the most important things in causal inference, because also this gives us a foundation to be then courageous to go and explore things that even if there's something that we don't know, we go out there and we try to get as much knowledge as possible and try to incorporate this knowledge into the process, and then hopefully get to some useful conclusions, right? Because what you said about the sensitivity analysis, won't be able always to get very narrow estimates, but in many cases we just can get to useful conclusions, which means conclusions that will allow us to make an informed decision.
Mhm.
You also mentioned in the beginning the importance of assumptions and knowledge in the process of causal inference. In one of your recent papers with Carlos Mejide, in the abstract you write at the end, that's the last sentence. I thought that was a sentence that really drew my attention. The sentence says, "This shift from identification under assumptions to identification under observation redefines how the problem of causal inference is approached." Can you share with us a little bit more about what's behind this? What's behind this sentence? What's the logic there?
Anyway, to just hit home, as you said, the transparency is clearly very important. And that's also, I think, where, it has to be reproducible. I think it helps you to write out that whole roadmap, the steps you took. So all that is part of the transparency. At the end, it also has to be good. You can be very transparent and you say, I did this, I did that, but then nobody knows what of it because it makes all these weird assumptions, right? So it's a really that's why it's often the discussion is often not either or. It's always all of it has to be good. Every step has to be carried out very carefully. But yeah, so it's a combination of transparency and high quality methods as part of it. That's why for me the FDA is kind of an important demonstration almost for science because they have to do approvals. These approvals have to be based on a priori specified analysis. And so that's challenging, right? How do you do such a sophisticated submission which is not a standard logistic regression anymore? It's using the state-of-the-art in machine learning, and it all has to be a priori specified. There's like target maximum estimation. So that is a very challenging thing, how to do that. And I think if you can carry out such analysis in that context, under regulatory guidance and approval, then that's a high standard, a very high standard for your analysis regarding everything you said, the transparency, dealing with every level of uncertainty. And so for me, that's a very beautiful demonstration project in a sense of how are we going to exactly do that and how are we going to be successful. But anyway, that was more of a side for now. But you were talking about this paper, which is about instrumental variables. Yeah, I mean, maybe the kind of shift in thinking in that paper is that normally we say, like let's do the simplest case. You observe on every subject in your sample baseline covariates. Then there is some instrument, right? That could be something randomized. It might be actually a treatment in a randomized trial. But it could be something else, like some kind of recommendation you're giving to a person in an observational study, but it's kind of random. So we call that an instrument. And that's supposed to encourage a treatment. That you say, like I randomize people to treatment, and then you suppose that people actually do it, but they might be non-compliant, right? Or similar, you might work with a doctor and you give them a recommendation with your system, your algorithm gives them a recommendation. That could be an instrument. That might have been randomized, but then the doctor still decides what he does, and that's then the treatment. And so you have then these data sets, baseline covariates, an instrument which you understand it's randomized, and then there is the actual treatment, and then there is the outcome. It's easy to estimate, or at least it's nice to estimate the causal effect of the instrument, because the instrument was randomized, and so you can actually rely on the no match confounder assumption, and so everything can be beautifully done. On the other hand, what people normally do, they would say, okay, I care also about the causal effect of the actual treatment. So I'm going to ask myself the question, for example, what's the ATE? What happens if I force everybody to give the treatment versus what happens if nobody takes the treatment, and what's the difference? And then you say, okay, darn, treatment is subject to unmatched confounders. I have to use some kind of identification result based on the instrument. And that will then naturally rely on all kinds of assumptions, which are not always easy to sell. Okay, so what we did here is said, let's not do that. Let's actually just say, what can we identify? For example, the causal impact of any kind of intervention on the instrument. These could be stochastic interventions as well, right? Mm-hmm. They could be static interventions, but also stochastic interventions. So if I put any kind of stochastic intervention on the instrument, I can identify what's the so-called post-intervention distribution of your outcome. So what will be the mean outcome, for example, under a particular stochastic intervention on the instrument. But any intervention you do on the instrument changes also the distribution of the treatment. Right? Think about the medical doctor. You are giving the person a recommendation that influences the doctor. And so it changes the way the doctor is going to assign treatment. So what really happens if you just say, if I assign an intervention to the instrument, it implies an intervention on the treatment. And we can actually identify that. So we can actually write out what for any given so-called conditional distribution of the instrument given the covariate, so how you assigned it, you can imply a conditional distribution of the treatment. And so really what we're then getting is that we can actually identify, without any assumptions beyond the instrument, the mean outcome under any of the stochastic interventions on the treatment implied by a stochastic intervention on the instrument. So we turn it around in that way. We are not asking, how can we identify this particular causal question, like causal effect of treatment, and then need all kinds of assumptions. We say, no, what we can identify is the mean outcome under any kind of stochastic intervention on the treatment corresponding with a stochastic intervention on the instrument. And so we have this mapping, which maps a conditional distribution on the instrument, which is a stochastic intervention instrument, into the corresponding conditional distribution on the treatment, which is a stochastic intervention on the treatment. And so now we do get actually identification results for any kind of like mean outcome under any of these stochastic interventions. So if you, for example, take two interventions on the instrument, two different ones, right, they imply two stochastic interventions on the treatment. And so it gives some kind of difference in mean outcome, right? A contrast, a causal contrast of two treatment regimens differences. And then on top, you can say, that's already nice, so that we can actually really, write down what we can learn from the data and the kind of causal effects we will see. But we can also ask the question, so what will be like, among all these possible stochastic interventions on the treatment we can identify, which one is closest to what we really like to do? And so we can learn that too. And so this way, we are not getting into assumptions we don't know, we don't trust, or don't feel comfortable with. We just literally learn from the data what we can get and how close we can get to maybe what you desired, but either way, you get all kinds of interesting results. And I also think that's actually quite natural, right? If I let's say I'm developing a recommendation system with some fancy algorithm for doctors, and I know I will randomize that. It might have different levels. It's not necessarily binary, these things. There might be all kinds of choices you're making. Well, I kind of want to understand, if I do this, if I assign my recommendation in this way, how does it impact how the doctor actually starts treating? That actually we can work out, and there's a formula for that. And so we can actually learn that. It's kind of the reality. This is how it works. You have your recommendation system, and you can influence through your recommendation system how you intervene on that, how the treatment changes of the doctor. So that itself is an interesting thing. That will also then give you the corresponding, causal effect of that way you were able to influence the doctor on the outcome. And obviously, you will see that if your recommendations is hardly influencing the doctor, then you will have no impact. And you will see that also from the actual, treatment regimen implied by your regimen on the instrument. So I think it's just the reality. You're trying to answer questions you can actually get to.
I think that's really, really great and really interesting. And also my feeling is that your thinking here is highly practical in a sense, right? You really think about what would be the value of something like this in the real world, where our information, we know our information is imperfect.
And also, people were also they came to me and asking questions about how do we do this in the time-dependent setting? We have time-dependent treatment. And again, there, I think it's also very natural. So we'll have a paper following up on this, the one you saw, where we get into that as well. And it's just somewhat of a philosophical difference with some people who are very much, I might have with Uday, I might have a discussion, and he would be like a really clean definition of the causal quantity you care about. And then just, then if you can't identify, you can't identify it. Mm-hmm. And I'm willing to give up some of the interpretation of the causal quantity, but actually something you can actually learn instead of relying on these assumptions. So that's what this gets at, right? So it tries to push the definition of what you're trying to learn, the causal quantity, towards what's actually learnable. And that's it has always been the way I talk. So in that sense, we often think in terms of what are the causal questions we can actually answer for which there's support. And this is an example of that where it's perfect support in the sense you have no gap, causal gap. So these are the kind of causal questions we can truly identify without any causal gap, meaning you get true honest inference for it. And then at the end, you can interpret it. And yeah, I agree. I think that is more the reality. That's the things you can actually learn, right? And depending on how good your instrument is, you might be able to have more influence on the treatment regimen of the doctor. And in this way, you will also develop more regimens you can learn because you are able to change it so much with your instrument. And therefore, you get now all kinds of causal questions you might even desire from the get-go. So yes.
You said about this practical aspect, the applied aspect. When we met before, I remember you also told me that this practical perspective has always been important for you. Can you tell us a little bit more about your personal history and how this idea of practicality, of applicability played a role in your development and your thinking about causality?
I've always, anyway, just as a little background, I did my degree in mathematics, and then I did a PhD in theoretical statistics, working with Richard Gill. And Richard Gill had a big impact on me because he's really also that kind of person who he's a deep, mathematically trained theoretical. I mean, he has done incredible work. I mean, you can look at this work on counting processes and so on, but really establishing deep probability foundations and all that. But he's always very interested in the real world. Now that's also what I had. I've always, at the end, I'm not looking for theoretical problems to just have fun. I'm looking for real world problems which need to be solved. And then it happens to be that many times these real world problems are very hard. Right? And then you have to come up with theory. And that might be sometimes deep theory to do it right. And so that's where I come from. So I never start with the toy problem. I always start with the real world problem and go from there. Yeah, that's also why I automatically got attracted, during my PhD thesis, I worked on things like bivariate survival, function estimation based on bivariate right sensitive data or multivariate right sensitive data, and how to analyze these estimators and how to repair the non-parametric maximum likelihood estimate, which breaks down in these problems, and so on. And then I met Jamie Robbins. He came actually to there was a workshop at the end of my graduation, and so people like Peter Bickel were there and John Wellner and so on, and also Jamie Robbins to just kind of also do give some talks and lectures and so on. So that was a nice way to get these people together. Jamie gave a talk there and essentially said, Mark, it's fun to work on bivariate right sensitive data, which, by that point in time, I was pretty proud because it was like a challenging problem for decades of how to do this, the efficient estimation. And he said, Mark, who cares about this? Right? I mean, who cares about the bivariate right sensitive data? In the real world, that's not the data you are going to have. In the real world, you're going to have longitudinal complex data structures. This is the real world. Patients enter your study, you have a whole history, they randomly drop in for visits, you have doctor's decisions. Doctor's decisions are made on the history of the patient. There might be dropout, and the dropout might be informed by the past as well, and so on. So how are you going to do things there? And that's suddenly in world of data, level of data, in the dimension of data, which immediately pushes you out of the comfort boundaries. There's nothing convenient about it. It's not like I can just simply fit a simple parametric model. So that's where I started working with him. And mostly what I did at the time is trying to learn what he did. Right? He had all these papers nobody read, essentially, because they were, very hard to read. So I started reading the appendixes and this work with Andrea Rodnitsky and so on. And so we got into thinking about how to do some of his methods into problems where you never observe the complete data, interval censoring, that kind of thing, current status, and so on. But I was automatically attracted to the kind of real world approach Jamie Robinson had to really addressing key questions in the real world and how to answer them. Anyway, so that's very much aligned. And then, of course, with that came another journey, how I eventually got into things like target mix and likelihood estimation and so on. But yeah, it's always the drive comes from the real world. And if you look at some of my contributions, yeah, they're very much in that spirit, right? If you think about the kind of, when I studied cross-validation, for example, and I got into this thing like super learning, I mean, that's a theory not developed for like least squares regression or something, or linear models, or no, it just says, what's the real world out there? The real world out there was people want to use, and I wanted to use machine learning. You have a whole range of machine learning algorithms. Which one are you going to use? It's not like model selection, because it's not, the algorithms are not even using a model. So it's not bandwidth selection. It's not variable selection. It's estimator selection. And so I define it as estimator selection. You just have a bunch of algorithms, you have to choose among them, and they have a certain goal of like learning a prediction function or something like that. And so how do you choose among them? And what's the theory doing that? And so that became like a generalized way of doing cross-validation for any kind of estimation problem, any kind of machine learning algorithm, and then developing the theory, which shows that cross-validation is the optimal way to do it. And it has the so-called oracle property and so on. But it is immediately very general, very applicable to the real world. And it gave, in particular, this super learner, which was saying, you know, this is the way we should be doing machine learning. We shouldn't be betting on one algorithm. We should not be competing like, I like this, you like that. No. And if people come up with a new algorithm, great. Let's include it in the library and build an even more powerful algorithm thanks to that extra contribution. And so this way it becomes a very practical system of learning, which integrates all the advances and really handles the real world. Right? Mm-hmm. And so that's the kind of things which you will see is that in the kind of works I've done, it's always from that perspective, that it's really applicable to solving these real world problems. And that's also kind of how the theory I develop adapts to that challenge.
You mentioned super learning, and that's a part of a broader framework that you have created over the years. And I'd love to talk about this. But before we move there, I have one more question to you. Mm-hmm. You mentioned Jamie Robbins many times during our conversation today. And I always had a feeling when I was reading your works that Jamie Robbins had a big impact on you and your thinking about causality. There's also something very interesting in your works that I do not that often find when I'm reading other authors. You are taking Robbins' thinking on one hand, and often you mix it with thinking coming from Pearl, for instance. And you kind of seamlessly blend these two perspectives in your writing. Where does this come from?
Yeah, I'm also very pragmatic. Yeah, so I'm not very much into, you don't get me very excited to be part of a debate if we should be using structural equation model or the Naden-Rubin model, because for me, they are both interesting way of modeling the real world. And sometimes, to be honest, I feel more comfortable with one, right? Like a structural equation approach. And sometimes I really like the just simple, missing data structure on a bunch of potential intervention-specific processes or outcomes. So I'm willing to switch between one and the other. At the end, I define a causal question, the same causal question, and at the end, they give the same statistical estimate and all that. And of course, people have different contributions, right? Like Jamie Robbins, of course, did a lot of work on also the causal model development, but also a lot of estimation. And Uday Kurl was much more on the structural equations modeling, and then also getting identification results and algorithm for identification results and so on. So yeah, these are different brilliant people. They have their own views on things, and I happily learn from them and talk to them and interact with them. I don't feel very much ever to belong to a certain camp, and often there's something to learn from different people. But I don't know if that touches on what you mean. But
I really love your perspective, because at the end of the day, these like potential outcomes and structural causal models, these frameworks are largely interchangeable, right? They have almost the same meaning, with some exceptions maybe. But I really love reading authors that just blend them wherever something is more useful.
Yeah, and an example of that is, you're right. For example, I remember, it was a student of mine, we were talking about some kind of like mediation formula. And the mediation result at the time was, in particular, the one from structural equations. And they would put down an identification assumption in terms of structural equations. But then, when you write it on a piece of paper and you do it in terms of potential outcomes, you see that you can weaken that quite a bit, right? And it makes it very specific about a very conditional mean, right, of certain treatment-specific outcomes and some kind of conditional independence. And it becomes suddenly very different. But from a structural equation model where you just look at the graph and try to learn the identification from that, you wouldn't see that. Because that gives identification results for general post-intervention distribution, not very specific for certain very specific questions, such as a contrast of a mean outcome under different regimens. And so that's where you see that by just switching from maybe something very nice about kind of looking at graphs and learning identification results from that also you have to acknowledge it's also limited that way, because it gives you too strong assumptions, which can be often weakened once you care about something very specific. And so that's kind of the switching I do naturally do, and I'm happy in both worlds. And then you do see the benefit in some cases from one versus the other.
Yeah.
And so so depending on your goal, you might switch from one to the other.
That's a great perspective. I really love it. I'm a huge fan of Berkeley's framework. I always emphasize this. I think it gives a lot of clarity and also gives a lot of opportunities for transparency, right? And in particular, transparency with people who are not necessarily technically trained or technically skilled. I work a lot in industry, and so causal graphs are just like such a convenient way to communicate with business people, for instance.
Exactly.
And they find them, after a while, maybe after a second of confusion, after years of talking to data scientists, coming from just machine learning and so on, when they grasp the idea of a causal graph, it becomes so intuitive that it's really incredible. At the same time,
where you see the benefit of people who are less mathematically inclined. They suddenly have a framework where they can get a head around and make progress and embrace it. And so that's why all these different views and approaches have their utility. Even though they be perfect for every purpose.
I also appreciate very much that what you said, right? Sometimes if we look a little bit closer from the point of view, maybe a little bit more of the estimation point of view, the identification point of view, we can notice something that is just invisible when we look from this purely structural point of view, right?
Yes.
And so just make our lives easier. That's really great.
Yeah.
Mark, I wanted to go back now to what you said before. You mentioned super learners, and super learners are, I think it would be fair to say, it's a part of a broader framework that you've been working on for years, which is called targeted maximum likelihood estimation, or TMLE. What is TMLE about, and what inspired you to work on this and put so much effort, so much work into this framework over the years?
Yeah, so that has been kind of one of the biggest drives of my journey, has been, given a statistical estimation problem. So you have a certain study design, a certain type of data you collect, certain features or complexities such as dropouts, missingness, informative monitoring, time-dependent treatment assignment, treatment by indication, and all that. Given the statistical estimation problem, well formulated, you know what your statistical estimate is, you know what your statistical model is, but we also know they're not parametric models, because I call them realistic statistical models, meaning you're taking it serious. You make assumptions which you can defend. How do we, for such statistical estimation problems, how do we construct the best possible estimate? And so that has been my journey and my goal. So that's also how I think, right? I'm literally always thinking that way. So it's not like I'm working on a very specific problem in that sense. Yes, they are, of course, also work on them. But in my mind, I'm kind of philosophically thinking, how do we do this? How are we going to construct, really optimally learn from data? That has been a long journey. And I started with understanding non-parametric maximum likelihood estimation in reasonable models, but still non-parametric. And so that's what's like my PhD thesis was, is to understand, they called it NPMLE, non-parametric maximum likelihood estimation. In things like Kaplan-Meier is a non-parametric maximum likelihood estimation function based on right sensitive data. Then I worked on bivariate right sensitive data and so on. So that helped me to develop a lot of theory and insights, how to analyze estimators. And so it gave me a lot of tools, mathematical tools to understand how to think about estimators, how to analyze them, and all that. So as I pointed out, Jamie recognized that kind of maximum likelihood ends quickly because you can handle it a little bit in certain dimensions, but quickly it becomes too much. So for most statistical, like even when you have right sensitive failure time data with a single continuous covariate, it already becomes a problem. How to do non-parametric maximum likelihood estimates. So you have to start getting beyond MLE or NPMLE. And so that's where I learned from him about the estimating equation approach. And that was, it's a whole story about whatever he called it, orthogonal complement of the nuisance tangent space and the class of estimating functions. And you have to orthogonalize these estimating functions with respect to the nuisance parameters. And that's nowadays, they call that also double robust machine learning, by the way. But that came after that. Right? That what Andrea and Jamie had done was that whole orthogonalizing of estimating functions. And then, one estimating function would then be the best one, and that corresponds with what we call the efficient influence curve, the canonical gradient of the statistical estimate, really. And I wrote a book with Jamie, which was Unified Methods for Censored Longitudinal Data and Causality. And when I was writing that book, and also based on all the work based on that and before that, and looking at other people, how they were experiencing things, and postdocs spending a lot of time implementing things and so on, it became clear that this approach was theoretically appealing. It's the double robustness people refer to, but it also has some serious flaws. And also created kind of two camps. It created the camp of people who want to live by the likelihood, and that includes the Bayesians, right, who work with models and model selection, and so that was one camp. And then there was this kind of estimating equation approach camp with double robust estimation. And maybe theoretically you could say that double robust estimation was maybe better. But at the same time, the people who were working with these likelihoods and doing MLE and Bayesian, they felt pretty darn good about what they were doing because they felt it was quite robust. And that's because, you're learning kind of adaptively your likelihood. And at the end, you map that into what you care about. What do I want to learn about my stochastic system I'm learning? And if you're trying to learn a probability, then you will end up with a probability. And if you're trying to learn a difference of probability, you end up with a difference of probability. And so all the kind of bounds are naturally taken care of because all you do is learn the density of the data and probability distribution and then plug it in. And so you get naturally robust estimates. They don't do something crazy. And that was not the case with estimating equation approach because there you have this inverse weighting going on. And because of that, you might end up with estimating equations which have no solutions or have solutions which are like negative or bigger than 1 when they're supposed to be a probability, and so on. And there was another thing is that actually that estimating equation approach doesn't always apply. There are lots of estimation problems where the so-called canonical gradient, which is kind of the optimal estimating function in that world, is not an estimating function. It's not something you can write as a function of the parameter of interest and the nuisance parameter. You can just not do that. It depends on the data distribution, but you cannot split it up in parameter of interest and nuisance. And so then it doesn't even work. So by then, the history was in the 70s and 80s, 1970s, 80s, you had the so-called one-step estimator, which was an efficient estimator. And what that did is it constructed a plug-in estimator. Right. Again, keep in mind the statistical estimate is just a mapping applied to the data distribution. So a plug-in estimator takes an estimate of the data distribution, which is in your statistical model, and plugs it in that mapping. And that gives you then a plug-in estimator. And So the one-step estimator constructed an initial plugin estimator and then added an empirical mean of what we call the canonical gradient. Now, the canonical gradient is something it's like you take your statistical estimate, think of it as a mapping from the density of the data to the real line, compute some kind of derivative, we call pathwise derivative,
Mm-hmm.
and that derivative is characterized by a gradient. That's called the canonical gradient. So the main lesson is you can analyze the statistical estimate as a function and figure out that so-called canonical gradient. And that canonical gradient is just a function of the unit data structure and, of course, at what data distribution you're doing it. So it's a function of P, the data distribution, and of the data structure you observe on every unit. And so that's something you can actually find, the canonical gradient, for every statistical estimation problem. We can do this differentiability and figure it out. It's a very important object. I often refer to it with my students as the most important object because it tells us that there's efficiency theory, and it says that among all estimators which are well behaved, there's an efficient estimator, and it's efficient even only if it's so-called asymptotically linear. So if you can write the estimator minus the true estimate as an empirical mean of the canonical gradient plus something negative. And so that's why the canonical gradient is also called the efficient influence curve, because the influence curve, when you say an estimate is asymptotically linear with a certain influence curve, that means estimator minus truth behaves like an empirical mean of that influence curve.
So there's a connection between statistical efficiency and properties of the canonical gradient.
Yes, the canonical gradient defines an efficient estimator, the best estimator. And so what the one-step estimator was in the 1980s was plug-in estimator plus the empirical mean of the canonical gradient at the initial estimator. That was the one-step estimator. Estimate equation says the canonical gradient, I want to think of it as an estimate function. And then TMLE was what came after that. And I was inspired because I wanted to have the properties, theoretical properties of these double robust estimators, and that they have theoretically, asymptotically, they're correct, they're asymptotically efficient, all that. But I also wanted something which generalized maximum likelihood estimate, that we wouldn't have two camps anymore. It would, if you want to be a maximum likelihood, you can be a maximum likelihood, except sometimes it doesn't work. So now you have to, but you still essentially stay as close as possible to maximum likelihood. And so that's what we call targeted maximum likelihood. And so that was something we wrote in 2006 and a paper, and that was inspired by the limitation of both maximum likelihood estimation as well as the kind of, what you might nowadays call double robust machine learning or the estimating equation approach and the one-step estimating. So all these previous approaches, and then TMLE, is then the kind of thing which came out of that. And what TMLE is, it's still just a plug-in estimate. So it's just like maximum likelihood. You learn the density of the data or the relevant parts of the density of the data, and you plug it in your estimate, right? Like, for example, you care about an ATE. An ATE can be written as the mean clinical outcome under treatment and conditioning on covariates minus the mean clinical outcome under control, conditioning on these covariates. So that's the difference of two predictions under treatment and control at a particular covariate profile, and then you average that. That's how you can identify the average treatment effect. TMLE would say just estimate these conditional mean outcomes, but with machine learning, but update them, target these fits towards the purpose, and then plug them in and average them. And so that's a plug-in estimator, just like maximum likelihood would do, right? In maximum likelihood, normally use a parametric model. It would estimate the outcome regression with a parametric model, gets for every subject in your sample the prediction of the outcome and the treatment, and control take the difference and average. That will be a parametric model-based estimate. So TMLE is also doing that, except it uses machine learning, but also uses the target maximum likelihood step to make the machine learning tailored for its purpose, which is evaluating the statistical estimate. And then it has all the theory, right? And better. We can use state-of-the-art machine learning, like super learning, still get statistical inference, and still stick to normal plug-in estimation, which is very natural. Of course, people, once they're used to something unnatural, they think it's natural, but it's not natural, right? If I tell you what the statistical estimate is, then you say, oh, so what do I need for that? Oh, I need this and this and this. Oh, let me learn it. Oh, I plug it in. That's natural. That's while writing down a canonical gradient as an estimating function and setting the empirical mean equal to 0 is not natural. right? You might be trained that way, but it's not something like, again, maximal likelihood wouldn't do that. So that's why, target maximal likelihood, if maximal likelihood would work, then target maximal likelihood would just use the maximal likelihood as initial estimate, and then it doesn't do anything. So you just get maximal likelihood. So it generalized maximal likelihood, but now we can incorporate all the machine learning and therefore generalizes it to realistic statistical models. Yeah, that was a paper we wrote in 2006. And then always you wait, because you think maybe there's something wrong with it and we'll have to adapt again. But it was just a very powerful framework. And it kind of opened up, it's a very general, flexible framework which allowed us to essentially handle any kind of challenge. So whatever next challenge came up, we could always make it work within this TMLE framework. And what helped a lot is just that you have a likelihood, you have a criteria. And so you can tailor your decisions towards that.
I wanted to pause you here for a second because you said a very interesting thing here, a few interesting things. That the first one is that this work on TMLE was, in a sense, ecumenical, right? You said like, oh, we don't have to make this decision. We don't have to subscribe to just one camp. We can have, in a sense, best of both worlds. And so that seems to me like yet another example of you looking beyond the popular demarcation lines between different camps and just taking what's useful and what's applicable.
That's of course also where my journey had helped, because I had worked, of course, on maximum likelihood. Then I got into the camp of estimating equations and all that, which was great. And then I was kind of part of that camp, also thinking, maximum likelihood will never work. But then you start also kind of, certainly if you start writing a book on it, you start, thinking philosophically about it. Am I on the right track? And that's often what you have to do in science, right? You have to continuously ask yourself, what am I doing? Does this make philosophically sense? My advisor would always say, you need to be able to, if you work on something and you think it's good, you should be able to explain it during a hike in a forest with a friend who's not necessarily the best trained person. You should be able to do that, because then it should be philosophical and it should be beautiful and it should be something you can explain. And if you start losing that, you have to talk about formulas and this and that, then something is off. Yeah, that's why you have to always step back and say, am I on the right track? Does this feel right? Is this something I can philosophically explain? And once you do that, then suddenly you start saying, this is really not that natural, that whole estimating equation approach. And it's not natural because you see that for most estimation problems, there is not even an estimating function. So you just know it's not natural, because otherwise the nature would just automatically adapt to it. So then I had the maximal likelihood in my history as something I understood. And then also understanding the limitation of the kind of the one-step estimator approach and the estimating equation approach. And then I said, okay, I have to go back to maximum likelihood and combine them so that I get both worlds. And that certainly was the right idea. And I think like some of my, like Marco Coroni, who was a former postdoc of mine, of course now at the University of Washington, he also saw like a reference in Van Zagel, who was a person in the 80s or 90s working on efficiency theory and even second order efficient estimators. And in his writing, you can see it written that he says, wouldn't it be nice because he was doing these kind of updates, like one-step estimator. You take an initial plug-in estimator, add an empirical mean of a first order canonical range, then you add another use statistic of another second order thing. And the thing is, of course, painful, because if you start adding things in, like your estimating probability, and you keep adding these kind of noisy objects, you have no reason why at the end it will be a nice bounded probability. So he recognized that, and he said, wouldn't it be nice if we can do the updating in the model space, update the density instead of doing it in the parameter space? And so he didn't say how it should be done, but that's he recognized how painful it is to do these updates in the parameter space. And so so it is actually really the natural idea to do target maximal likelihood as a way to do it.
Mark,
and that happens to be true, because I've seen it now. We are now in where are we now? 2025. So it is. This paper was written in 2006. So we're 20 years down the road, and if anything, it became stronger and stronger. So it's not like sometimes you start seeing things falling apart over many years because you see this problem, you see that problem. This is the opposite. It's just flexible enough to be able to handle the challenges we have to deal with.
When I listen to you and you talk about this targeting of the parameter, it brings to my mind the idea of double machine learning. You mentioned auto-organization and double robustness before, and so on and so on. So the ideas that are very close to that framework, which is a more recent framework. But it seems to me that your framework and double machine learning, although they originate from different sources, so to say, behind the scenes, they are very, very close to each other. Would you agree with this view?
In a way, I don't. Another way, I might. Right? Mm-hmm. Because again, this represents the difference between the augmented IPCW, they call it, right? Augmented inverse problem sensing weighted approach, which was Robbins-Rodnitsky, really, right? And then the double machine learning was doing that, right? They were using like an IPTW type thing and IPCW, and then orthogonalize it with, they called it Neyman orthogonalization, while Jamie Rollins called it orthogonal nuisance naming space. And then they create an estimator from that. And yes, they started talking about machine learning, which, was done, we did that early on, right? We have been using machine learning from the get-go when everybody was angry about it.
That's another way where you transgress the boundaries, the camp boundaries, right?
Against the camps, absolutely. Yeah, that was something which was not something you should be doing. You shouldn't be using machine learning and still think you can do theory. So I would say the double robust machine learning, and they have some novel ideas in that literature, right? Beyond the augmented IPCW or orthogonalizing nuisance scaling space, really. It's missing the piece, which was the journey where I went from estimating equation and one-step estimator towards plugging, and that's the TMLE. So they skipped, so they came after the TMLE. In that sense, it misses out on the TMLE. In some ways, yes, all these approaches are based on what we call the canonical gradient, right? Efficiency theory. Efficiency theory defines for us an efficient estimator. So now if you want to be efficient, you should be asymptotically linear estimator with influence curve, the canonical gradient. So all of them are aiming for that and succeeding in that under very similar assumptions. Mm-hmm. So in that sense, they're all related. But the one which really marries the whole world of maximum likelihood and SIF maximum likelihood, Bayesian, with the actual efficient estimation is the TMLE. Mm-hmm. Yes, there is a lot of similarity because all of them work with the canonical gradient. But then how you use the canonical gradient is the key, right? For finite sample performance. And you can use the canonical gradient in essentially three ways. One was the original way in the 1970s and 80s. That's the one-step estimator. Take an estimator of your target parameter and add the empirical mean of the canonical gradient at the initial estimator. Was number one. Number two, use the canonical gradient estimating function. That's the Robbins-Rodnitsky, augmented IPCW, and also the double robust machine learning. Number three, don't use the canonical gradient in that way. Create an initial density estimator. Create a little parametric path through the initial density estimator. Make sure it has scored the canonical gradient. The canonical gradient happens to be a score. So I construct a little parametric model with only one unknown parameter, or multiple sometimes. And I do a little maximum likelihood step. And that parametric model uses offset your current superlearner or whatever your fancy machine learning density estimator is. And it does a little parametric maximum likelihood, and then you get an updated density estimator, the targeted density estimator, and then you plug it in your parameter. These are the ways you can use the canonical gradient. And in that sense, they're fundamentally different. Mm. And that's where, from my perspective, that makes them very different because I know how important it is to stick to the likelihood and have that criteria to make your updates and really be a plug-in estimator in the end.
When somebody, a practitioner, is considering which type of estimator they should use, maybe if they should go with TMLE, maybe with something else, what questions should they ask themselves in order to make the best informed decision?
If you're asking me, right, I say use TMLE. But keep in mind, and that's because I did the whole journey. But of course, when you haven't made that whole journey, you might be part of a camp. And one camp, your PhD advisor was a Bayesian. So you're a Bayesian maximum likelihood, doing model selection, all that. Another camp is you were more into augmented IPCW. And you think that's what I should be using. And look, it has great properties. But if you're not belonging to a camp, then I can tell you, TMLE is the way to go. It is the future. And not because of whoever developed it. In essence, it's really a product of a huge academic group, right? Community. It's all built on all these advances from the 70s and 80s. It's building on the efficiency theory. It's building on the empirical process theory. It's building on all of it, right? And all the work of the Pearls and the Robins and so on. So this is not like a simple or side thing. It came out of it. It evolved exactly out of it, and it takes in all these advances. And also keep in mind, TMLE is not a single algorithm. It's not like, oh, I have a problem, I need to do the average treatment effect, or I have a survival data and I want to get the causal relative risk on survival at 5 years, right? So, I'm going to use TMLE. TMLE has lots of choices.
It's a framework. It's a
template for constructing targeted plug-in machine learning estimators with valid inference. And so there are choices to be made. There is, how do you write down your statistical estimate, right? Like, for example, in survival, you might write it in terms of the conditional failure time hazard. Okay, good. Let's estimate that conditional failure time hazard. How are you going to do that? What algorithm are you going to use? Like a super learning or highly adaptive lasso is one we like a lot, or both. Put it in the super learner. And then also, how do you do the targeting precisely? There are often choices to be made. Right? They all will end up being efficient estimates, but how you do things can actually be tailored towards your particular sample, because your sample size might be very small, or your sample size may be not so small, but there's a lot of challenging. Like there's a lot of positivity issues, we call them, right? That weights blow up. And so all these things can really influence what's the best way to do the precise targeting step, for example. And nowadays we have adaptive TMLE, so we kind of regularize the targeting steps to tailor it again for your finite sample, so you can get the best bias variance in the finite sample. So that's why it's not a simple thing like, oh, I'm using TMLE, let me grab something, because you can. Of course, most things have software now, and they have implementations, but they're often defaults, right? They're not tailored for your particular setting potentially. So you have to do some homework, and potentially there might be standard software packages which are giving you enough to work with. So that's why for me, it's not just, the real question is, from my perspective, how are we going to do the TMLE? And a lot of our research is about that. How do we set up a priori specified statistical analysis plans, including the specification of the TMLE based on for your particular study? And anyway, that's kind of where the software has to evolve as well, because this current software is often open source and not necessarily ready or maintained that way, or not necessarily tailored and not user-friendly enough. And so that's why I think there is a future for producing, robust industry quality software, but also user-friendly, so that these choices are kind of made for you in the right way. Mm-hmm. And that's also something I'm working on. We have a little company where we get into that, so that we can be advising on that, how to do this.
For people who are just starting and are maybe interested in open source implementations, what can they do? In my book, I describe one of the possible estimators, TMLE estimators. Now, but I'm not using any framework. This book is focused on Python. And at the time of writing, I was not able to find anything in Python. But I know that there are some things in R. Maybe they are also in Python. What would you recommend to someone who's just starting?
Oh, that's actually glad you asked. That's a good question. I'm not married to R. I'm not married to, but Python is great. It just happened to be, in the community I was, that R was kind of the language. So we programmed mostly in R. And so, yes, you can definitely find all kinds of R packages. Like, for example, there's the TMLE package for point treatment analysis, where you just want to get the causal effect of a single treatment on some future outcome where you might have missingness. So that's all included. There's also packages for survival data, like Surf TMLE, and there's another one, Concrete, we have. And then there's LTMLE, which is longitudinal causal inference TMLE with sequential regression approach. And there is now, but then, there are lots of such packages, because, all kinds of people do that. But like I have a student, Toru Shirakawa, and he has been programming what we call deep LTMLE. Mm-hmm. And that uses transformer and deep learning to do the fitting and still do the target mix likelihood and all that. And so that's done in Python. Actually, it has been much better. from a memory and computational perspective. So that's why I'm not married to recommending R. If you live in the Python world, go for it, right? And that's what he does. And so he has a very powerful implementations, and they keep evolving, and it's already available for people who want to use it. It's going to happen more and more. And I think you know more about that than I do, but that's I'm quite sure also these kind of things which maybe were not yet available in Python are evolving and getting more and more integrated there. And so at some point, hopefully, there's not much reason to necessarily go to R. Or I would be interested in your view more on if you think Python is just the way to go, or that both have their rights. It's great that all these communities start developing these products and have them available. And so far, my guess is that Python is just better when we get into really massive data and so on. But some R person might say, no, we can do that, handle that too. But it's just you have to know how to do it.
Yeah, of course. There are camps as well. I think R is great. I do my work mostly in Python, but I have R here in my laptop. And whenever I want to do quick something, check, build some quick data generating process and fit some, like models and so on, or maybe mixed effects models or linear models, I do it in R because it's just so much faster to write it in R. You don't have to import task models, something, right, or, and so on.
So we still have a little bit of strengths in certain areas.
Definitely.
And other areas like more the data science, they might have more advances in Python to deal with that's why Toru, wrote this whole thing in Python, and he seems to be quite content with it. But it really kind of depends on the needs.
Yes, I agree. So the name of the package is DeepL TMLE.
Yeah, DeepL TMLE. Yeah.
Great. We'll link to it.
It's actually quite an exciting because there was LTMLE. I don't know to what degree you're familiar, or the listeners are familiar with like the sequential regression approach for learning the mean potential outcome under time-dependent treatment regimen. And then you essentially can identify by sequentially regressing. You start with the final outcome, regress it on the most recent past, integrate out the lost treatment according to your intervention, make that your outcome, right? The predictions for everybody. Then you do it again, a regression, and again and then in that regression again, substitute for your treatment your desired regimen. And so you keep the sequentially regressing every time, evaluating your regression at the treatment of your choice, so that you end up with the mean outcome in the end under that treatment regimen. That's an approach, and you can do targeting of the regressions, and then you have the LTMLE. And that can be done for all kinds of extensions and so on. But DeepL still sticks to that kind of framework, but it doesn't do it sequentially. Mm-hmm. And so it's called temporal difference learning. It means you are simultaneously fitting all these sequentially defined regressions simultaneously.
That's why transformer.
And it's beautiful, I must say. It took me some time to figure out what he was doing, because I kept telling him, you cannot do that, till I understood what he was doing. But it actually is, it's beautiful. It's writing down one big sum loss over all time points, even though it's weird because you're using, in every loss, you don't know what the outcome is yet. So you define it in terms of your previous parametric model, essentially, which is this deep learning neural network model. And so at the end, it's this big sum of losses, squared error losses or whatever log likelihood losses. And then you do a gradient descent, but you only take the derivative with respect to for every loss with respect to the regression part and not the outcome part, which is also a model. So and then it works. Then you're solving the right score equations and everything works. So it's a beautiful idea, actually, and it really helps us because sequential regression had limitations because you had to kind of enough data, you couldn't have too many time points. And now with this DeepL TMLE, we can have arbitrary number of time points. We can handle continuous time. So yeah, it's really quite powerful.
That's really interesting. We'll link to the package in the description, in the show description, so everybody can check it. We're talking about transformers, so I have to ask this question. What's your take on LLMs?
On large language models?
Yes.
Yeah. No, that's phenomenal. I mean, I can see it with my my children, and like our youngest son. I mean, he's just living by it. I mean, it's like he's using it for everything, and they're getting very good at it. So yeah, it's ChatGPT is quite miraculous, I must say. And of course, things will evolve and get better. But yeah, it's not something we can deny or we can suppress, or there's no way this is happening, and it's happening fast. Of course, we need to think carefully about how things are evolving and what we trust and don't trust. But yeah, no, I'm a big fan, and I think it really was kind of a revolutionary step. So it's quite remarkable. It's quite remarkable. And I see it, how it changes, how people like I'm using my son as an example, how he just in a very playful way learns so much more than he could have learned on a college, right? By just continuously operating with this ChatGPT and playing with it and programming with it and setting up websites or whatever. And he learns all these skills, which, he didn't know how to do. So I think it's quite something.
So he's using it as a teaching partner, in a sense, learning partner.
It's a partner for him where he can, but in the meantime, he learns a lot about all kinds of things. But yes, it's definitely a partner where he collaborates with, in essence, and does all kinds of stuff and guides it to what he needs. So I think all kinds of people have become so much more powerful and by just having it as a partner than before. So it's quite something. And yes, and we are using it to some degree. I mean, like I said, the transformer we use as part of the estimation in DeepL TMLE, but also we are working on co-pilots for developing causal estimates using large language models. We have a student working on that. So it's certainly something, we think can be very helpful also for statistical analysis plan development and automating things. And again, like you said before, with the structured equations being more accessible for certain people than others, similar, these large language models can really make things much more accessible and user-friendly to carefully develop, go through the steps of the roadmap we talked about, right? And so really make that more automated. And think about the kind of things you have to think about. You can kind of train the large language model for being trained in that way of thinking and the way of answering, but at the same time, if it gets a little off, then it still has interesting things to say. So it's different from just writing a program, because then for a program you can just say, ask for this, then do that. But in this case, you essentially also train it to say what to do, but at the same time it has that automatic flexibility that it can still jump in and automate and answer things spontaneously.
Which can be a benefit and a risk at the same time, right?
Yes, that's right. That's the tricky, but yeah. So yeah, and that's why we need good ways to. I think it gives all kinds of new statistical problems to think about. How to evaluate, how to set up designs with ChatGPTs, how to optimize it for different purposes, and so on. So yeah, I think it's an exciting time.
Now I want to take a step back into the old school times and ask you, what are 2 books that changed your life?
To be honest, I'm not much of a book reader. I'm I write books myself, but then I never read them. So it's that bad. So I like the writing because that's a lot. That gives me really a way to concentrate and write up how I think and how the journey. I'm not much of a reader, including my own work. I mean, books which influenced me certainly were things like the Anderson, Boring-Gill and Keiding, counting processes. But also the Aad van der Vaart books influenced me, of course. And also the Bickel class of Rita Wellner. It's harder to read, but a lot of based on that work from people like that. Maybe a few came to mind. There are probably more. If anything, it's a weak point that I'm not much of an really. Now and then I look into things, but it's a lot. I let my students do a lot of the reading. To make sure we're up to date on the literature.
If somebody was could only read one of your books, which one should that be?
I would say the upcoming one, which is we have writing a book on the highly adaptive lasso in combination with TMLE. That will be, I think, a very powerful story. But yes, I would say, read the first targeted learning book, because the book with Jamie was quite difficult, unified methods. And then before that, multiple testing book we have. I would say the target learning book is probably the better one. Yeah, more coming.
Great. Yeah, I'm looking forward, and I hope our listeners as well. Mark, if you could give one advice to people who are interested in working on challenging problems, maybe in your area or some other area, machine learning, maybe statistics, maybe causality, what would that be?
I mean, yeah, I know, of course, what I'm kind of thinking about, but that's not necessarily, that's just one piece of things. And kind of part of my journey, to be honest, that's why it naturally flows. Because, TMLE was developed in principle, for what we call pathwise differentiable statistical estimates. So things you can estimate at 1/² sample size, so that you can get Causal normality and all that. And so what I've been working on over the last years is generalizing that to TMLEs for any function you're trying to learn. So including like a conditional treatment effect, or and still getting inference and confidence intervals and all that. Anyway, that's also my work on highly adaptive loss. So in essence, what's happening in my kind of research is I'm going back to maximum likelihood more and more. So it's like full circle. I started with analyzing maximum likelihood, then the estimate equations, target maximum likelihood using super learning, but now realizing that maximum likelihood also for the sake of machine learning is so important. And that highly adaptive lasso is an example of that. It's a very powerful machine learning algorithm, incredible theoretical properties, but all because it's like maximum likelihood under constraints on the target, on the functions or densities in terms of variation norms and all that. And then you can still get maximum likelihood estimated with your highly non-parametric, solve all score equations and get all the asymptotic normality and everything. So that's an area of research I think is still very interesting. But moreover, I would more say, understand the roadmap and attack the real world. And when you attack the real world, don't cut corners. Don't move towards immediate, I'm going to do this, or I'm going to do that. That's the whole idea of the roadmap. Really be real about the real world, translate it into an estimation problem, truly addressing the real world problem. And then you will see there's an interesting research area right there. Because it's never, it's not always that things you can use off the shelf. There will always be new challenges. And so I think that has been my experience, is you can get all kinds of interesting problems to work on by being out there in the real world and translating, and then see, oh, that's a challenge. Darn, how are we going to do that? Right? And then you have an interesting research area. So that's kind of my take. I think adaptive designs, reinforcement learning combined with statistical inference is another big one. Yeah, there's a lot out there. Overall, I would say we truly are getting to the point where we can start integrating in both the designs and adaptive designs the state of the art of machine learning, and still get valid inference and answer all kinds of causal questions. So
that's really great. That's really exciting. That's a really exciting prospect,
Yeah.
Before we close, what's your message to the causal community?
I actually think the causal community is great. I mean, I've seen so many young, smart people coming up. So I meet them now and then, and I'm impressed by how eager they are to really not just do something, but actually also understand it and learn it. And I like that. I like the fact that there are lots of people out there who truly want to understand what they're doing, be formal, formulate the problem carefully, and try to do a rigorous job. And of course, still, if you have the eye on the ball, some people are more on the pragmatic side, some are more on the data analysis side, some are more on the whatever side, computing, programming side. All that is important, and every contribution is important. So many people have to find their way, what drives them. That's also what I do with students. I try to make them figure out what makes them excited. And that's very different depending on the type of person. And so I think in general for the causal community as well, don't necessarily feel you have to belong to a particular camp or a particular expertise. Something has to fit you. And then once it fits you, then things will happen. And so that's, so just make sure you get inspired. If you're inspired, then you will learn a lot, and it will work out. So yeah, that's my take. Large variety of contributions are needed.
Thank you so much. That's a really beautiful take. I really love it, and I think it's a great closing for us as well for our conversation. Mark, I hope to have you again when your new book is out.
Great.
I'm sure we'll have a lot of topics to discuss, and I'm really grateful that you found time for this conversation.
Absolutely.
Thank you so much.
That's great. Thanks a lot for setting this off. All right.
Thank you, Mark.
Bye.